Hi, my name is Moumit Bhattacharjee, and this is the demo video of our project, the ALU calculator. So to start off, the first three switches control which operation is selected on the FPGA board, and then switches 13 to 16 are for input A, and switches 9 to 12 are for input B. So you can see how the two inputs are displayed on the left set of digits on a 7-segment display, and the result on the three most right digits. As you can see, addition is currently selected with 001, and it adding up inputs A and B and converting them from binary to decimal and then displaying that decimal value on a 7-segment display. Since the inputs are 4-bit values, the max value for the input for each digit is 1111 in binary or 15 in decimal. Next, you can see we'll switch to subtraction on the left side to mode 010. And you can see how the result is immediately updated to reflect the new operation. Next, we'll move to multiplication with mode 011. And you can see it can handle all different inputs, including multiply by 0 and a max of 15 times 15, resulting in 225, and everything updating immediately. Our next mode is going to be division with mode 100. Once again, instantly updating, and this mode will truncate the decimal, any digits past the decimal point, and we'll just show the whole number. And for numbers divided by 0, it will just simply display 15. The next mode we will have is modulo with mode 101. This mode will show the remainder of A divided by B. And we'll go through a bunch of different values and show out all different possibilities. Now we're going to move on to our logic modes, with the first one being XOR at mode 110. And with the logic functions, we convert the binary output to decimal, so we're able to display the result within the three digits that we allocated to the right side of the 7-segment display. Next, we have AND at mode 111. All switches are turned on. And then finally, our last logic mode is OR at mode 000 with all the switches turned off.
My name is Arnav, and today I'm excited to walk you through our FPGA-based ALU calculator project. So this project performs arithmetic and logical operations and then displays the results instantly on a 7-segment display. All right, so let's begin with a quick overview of the files involved in the project. So we have our constraints file, alu.v, bcd.v, clockdivider.v, decoder.v, and top.v. And in our simulations file, we have the test bench for the top module. All right, so let's first begin with an overview of our top module's structure and how it integrates all the submodules. So in this module, we basically manage all the inputs, computations, and outputs. And it takes the user inputs, processes them through the ALU, and then converts them for display using the BCD. and then multiplexes the 7-segment display to show the final result. All right, so let's first talk about the inputs and outputs of the top module. So the inputs include two 4-bit numbers, A and B, a 3-bit opcode for selecting the operation, a clock signal for timing, and a reset signal for resetting the system. And the outputs include a cathode signals for the 7-segment display and an 8-bit anode signal to control which display is active. All right. And one of the key responsibilities of the top module is to basically manage the multiplexing of the 7-segment display. So here's our state machine for display control. And so this module uses the 3-bit state variable to cycle through the 8 7-segment displays. And each state corresponds to a specific digit or like part of the display. So for example, when the state is equal to 3B000, the first display shows the result ones digit. And then when the state is equal to 3B001, the second display shows the results 10 digit. And so like this kind of cycling is all controlled by a slow clock signal from our clock divider module, which I'll get into later. And this basically ensures that the transitions are smooth enough so that it's visible to the human eye. So basically, how the multiplexing works is that only one display is active at a time, and this is determined by our anode signal. So for example, like when the rightmost display is active, the anode is set to 8B111110, and this basically means that the first display is, like only the first display is turned on. And then simultaneously, the corresponding BCD digit is sent to the decoder module, which I'll also get into later. And then it basically converts it into the cathode signals to light up the appropriate segments. All right. So next, let's discuss how the top module integrates the other submodules that we have. So for our ALU, the ALU module is instantiated here to perform like the actual arithmetic or logical operations. So inputs A, B, and the opcode are all passed to the ALU, and the result is an output as an 8-bit ALU result right here. So let's check out ALU.v really quick. So here in ALU.v, we can see how it takes two 4-bit inputs A and B and a 3-bit opcode to determine the operation. And it also outputs an 8-bit result and a flag for overflow. So for example, we can see here at 3B001 how it's performing addition by adding A and B. And then another example is that where we can actually see the overflow is for multiplication here at 3B011. So basically here we split the result into two registers, MSB prod for the higher bits and result for the lower bits. And basically the overflow flag is set off if any of the higher bits are non-zero. And then we also have our logical operations over here, which include XOR, AND, and OR. And these operations are pretty straightforward because you can just apply bitwise logic directly to A and B. All right, so now heading back to our top module, we can see how the BCD module here is instantiated and is used to break the 8-bit ALU result into three 4-bit BCD digits. So it would be dig1 for the ones place, dig2 for the tens place, and dig3 for the hundreds place. And so if we go to our actual module, here is the logic that that gives us the conversion. And for the logical operations, which produce just straight binary outputs, we just bypass this module altogether. All right. So heading back to our top module. So here we instantiate our decoder module. And so the decoder converts each 4-bit BCD digit or binary value into cathode signals to light up the correct segments of the 7-segment display. So for example, if the digit is 4D2, and I'll explain this by going into our decoder module. So 4D2, the decoder outputs 7B0010010, And this basically lights up segments to form the number 2 on the display. And then the last submodule that we instantiate in our top module is our clock divider. And here's where we instantiate it. And then here is the actual logic. And so basically what the clock divider does is it slows down the FPGA's clock signal, which provides a manageable frequency for displaying multiplexing logic. So without this, the display would cycle too quickly and our display would either appear blank or start flickering. So yeah, and in conclusion, like this ALU calculator project, it combines FPGA programming with hardware integration to create a fast, reliable calculator capable of performing a lot of different operations. So yeah, thank you for watching, and I hope you enjoyed this walkthrough.